Hi, in this short lecture video, I would like to describe, in particular, what's referred to as the electric potential energy. I might describe this as PE, for potential energy, sub-electric. And you might contrast this, and actually I'm going to show the analogous case again for what's referred to as the gravitational potential energy. And both of these types of energies, you would be used to the potential energy associated with gravity in units of joules. That's the same thing for the potential energy, electric potential energy. Practically speaking, the reason why this is important is because this is what is stored in batteries. That is, the electric batteries that people are very used to using that go into circuits like television remote controls, also in your cell phone, your earbuds, right? Any of these pieces of electronics that requires a battery, what's being stored in that battery when you so-called recharge your battery is you're not charging the battery. What you're actually doing is energizing the battery. Oops. Yeah, so that's a like kind of a picky detail. So you're not really recharging a battery. What you're doing is re-energizing. And I'm going to show you what's meant by energizing the battery. It's got to do with thinking about electric force. It's got to do with thinking about electric charge. And it's also got to do with thinking about work. If you recall work, the way that you calculate this is you imagine a force provided by some sort of external agent or system where that force is being applied on an object. In this case, we're going to imagine force is being applied on electric charges. But the work is not equal to the force, right? Because they're different kinds of pieces of information. The work is actually equal to the force times a displacement or a distance over which the force acts, right? So, yeah, and if you consider these things, you can begin to think about what's called the electric potential energy. And this is what's stored in batteries. Okay, so as an aside, or to get us ready, let's remember how it works out in the gravity picture, or when you're thinking about gravitational interaction. So here is, for example, let's say this is the Earth, and there is a box on the Earth, right? Some sort of massive box. And there is the gravitational acceleration in the background. It's the reason why there is a weight force acting on this massive object, right? Another reason that there's a weight force is simply because two different masses, so we're talking the mass of the Earth and this mass right here, right? These two masses are attracted, right? So there is an attraction. And this is because gravity, the gravitational interaction is happening. It's attractive. So remember that I described some sort of external agent that's going to be able to do work. So this is work done by some external agent. So that external agent, in this case, in my gravity picture, is a person. And what this person does is they walk over and they pick up the box. And when they pick up the box, after that happens, right? This is the drawing that's on your screen now is before the work is done. And the drawing that I'm about to draw is after the external agent does some work. So here is the Earth again. So I'll just say, here's the mass of the Earth. And the box is up here, right? And it's been raised through some distance d. And what has happened, right, you could even draw in the person. So what they've done, or what they've managed to have done, is to push the box upwards or push the Earth away from the box downwards, right? But ultimately, they applied some sort of force. This is the force by that person, and it was applied over the distance d. Now, if you really think about it, and this is interesting, the force by the external person was upwards, and this displacement, this distance, was also upwards, right? This force was applied upwards. So when the two directions match, that's considered a work that is positive. And whenever the work done is positive, then you can imagine that the energy increased. And that's how we understand what happened to the box, actually, right? So the box used to be close to the Earth, and now the box is further from the Earth, right? And that requires a positive input of work, which causes the gravitational potential energy in our system to have increased. We increase the energy, right? And this particular kind of energy is called potential energy. All right. So a keyword or a key issue that's going on is the fact that gravity is attractive. It is never repulsive. So what this means is gravitational potential energy only ever increases if masses are forced further apart. I hope you can see that. Gravitational potential energy increases whenever masses are further separated. So that's because it's attractive, right? Gravity is attractive. And so, so the way that you store up gravitational potential energy in this attractive interaction is you just separate things, right? Make them stand further apart, which is what this little person just did in this cartoon. So in the case of electricity, electric forces, between charged objects they can be attractive, right? Just like gravity. And this would be, for example, what would happen if you had, for example, a negatively charged object, right? We could say that this is Q1, right? Charge number 1, and a positively charged object nearby, right? We could say that's called Q2. And the interaction between these two charges is positive. So if a little person came in and further separated these charges, so they made that situation look instead like this, right? In this transition, like if you go from this drawing to this drawing, then this is called an increase in potential energy, but it's the electric potential energy, right? Because you took two things that are attracted towards each other and you caused them to be further separated. On the other hand, if instead you started here and went this way instead, so you had two oppositely charged particles that were kind of far apart, right? There was a big distance between them, and then you allow them to come together, then this is a decrease in electric potential energy, right? And that's the case of attraction, just like gravity. But because electric forces not only can be attractive, they can be repulsive, then we have to think a little bit more about how to increase potential energy. So for example, what if we had two negatively charged objects? Here's charge number 1, and here's charge number 2. They happen to both be negative. And so how do we increase the electric potential energy? And the way we do this is we push them closer to each other. Right? That's how we increase potential energy between two objects that repel each other instead. Right? So if you were going to consider, say, work done by some external agent or person, you could imagine there's a person on standby ready to walk over and push on this charge and push on it with a force this way, right? That's the force exerted by this external person over here, right? And if you're actually pushing them closer together, then the way the displacement happens is also towards the left. And whenever the force direction and the displacement direction are the same direction, that work done is positive, which results in increasing the energy. And in the particular case that's going on, the type of energy that's being increased is electric potential energy. This very same scenario plays out, for example, if you have two positive charges. Let's say this is called like QA, and this is called charge B. And what's interesting, so if you push them closer to each other, then you increase the potential energy. So the potential energy increases. Whoops. And if you allow them to get further apart, the potential energy decreases instead. In batteries, the way the energy is stored it's stored in the separation of charges. So in a sense, as you use a battery's energy, its electrons and protons are essentially getting closer together. right? That is, oppositely charged objects are getting closer to each other. So this battery, when this is happening, what's happening in the battery looks like, let's see, oops, it's higher up. It looks like, I'm so sorry. Oh, it looks like this case. I'm swiping past it. So as you use the energy in a battery, which has a bunch of positive charges and negative charges that are kind of far apart, as you use the battery, they all get closer together. And one way this can happen is because of how chemistry happens, right? Chemistry is essentially how, for example, some molecules that you start with exchange atoms with each other such that the overall change is the electrons are simply closer to their protons, right? So it's like a reshuffling of which atoms are connected to which. And one of the basic results of chemical reactions is electrons can be closer to protons. Yeah, so, oops. So down here, as you use the battery's energy, the electrons and protons are getting closer to each other. And then you can imagine the other version of using a battery is actually recharging the battery, or actually, and you know this now, it's re-energizing the battery. If you like re-energize your battery, what you're doing is you're taking all of the protons and electrons are separated. So you sort of undo, for example, in the chemistry battery, you undo the chemistry that happened while you were using the battery. So now in this case, when you re-energize the battery, you further separate the protons and electrons. Exactly how that happens is quite a detailed process, but if you're curious, you can look up very instructive, simple videos about various different types of batteries, including lithium-ion batteries and also lead-acid batteries. So lithium-ion, this right here is a modern technology for a battery, but also like older technology batteries are lead-acid batteries, and you can look up what's common and what's different between these two battery technologies. These aren't the only battery technologies. There's a lot of different battery technologies.